Welcome to the Rich Report, a podcast with news and information on the world of high-performance computing. Today, my guest is from Extreme Networks. We have Derek Granath. He is the Senior Director of Product Line Management at the company. So, Derek, welcome to the show today.
Thank you, Rich. It's a pleasure to be here.
Well, thanks for coming on, Derek. What I thought we'd do is go through your slides, and then we'll do a Q&A at the end.
That sounds great. So what I'd like to talk about today, Rich, and to all of you out in the audience, is interconnect options and alternatives for high-performance computing. And I'll talk specifically about Ethernet and how we can accelerate the high performance of the interconnect using today's high-speed, low-latency Ethernet technologies. Looking at the agenda slide, we'll talk about data and how people are using data, and all of the data that's being collected is pretty useless unless you can transform that data into real information, useful information. And that's where high-performance computing and big data analytics comes into play. We'll talk about high-performance computing interconnect challenges and the alternatives that are out there. And I'll talk specifically, as I mentioned earlier, about high-speed, low-latency Ethernet and how it's continued to evolve and is approaching the latencies and the performance of other alternatives such as InfiniBand and some of the proprietary interconnects that are used in HPC. And then I'll finish up with a few architectural examples using some of the solutions that Extreme Networks provides. So first, let's talk about data. And I'm moving on to the next slide here. How much data? The world generates 2.5 quintillion bytes a day, or about 57 billion 32 gigabyte iPads worth of data every day. That's a lot of data. If we look at the next slide, you've probably all heard this statistic before, that 90% of the world's data has been generated in just the past 2 years. So we continue to generate an unbelievable amount of data, and that data continues to be stored. And again, to make it useful, you've got to do something with it. You've got to process it, which means it's got to be moved from a storage array to a database server to an application server, and ultimately to some sort of a presentation server that delivers a result to a user in a reasonable amount of time. And we'll talk a little bit more about the types of data that people are storing, including structured data and unstructured data. So when I look at the data analytics challenge on slide number 5 here, when I think about big data, and not all of high-performance computing is the same as big data, but a lot of high-performance computing is, of course, analyzing a lot of data. I think about tens or hundreds of terabytes and even petabytes of data. I think about tens of billions and even trillions of data inputs or records. And that's the type of workloads that big data analytics and high-performance computing challenges are looking at today. If I look at slide number 6, the really interesting aspect of some of the analytics capabilities that are available today that weren't maybe 3 to 5 years ago is the ability to analyze unstructured data. And just a quick definition, structured data is that which fits neatly into a traditional relational database, such as the metadata of an email, the from line, the to line, the subject line, the fact that the email has an attachment and maybe even the name of the attachment. The unstructured data is the data that is more amorphous. So it's an embedded video clip or an embedded MP3. And this example, you now know that one of my hobbies is playing in a rock band on the weekends. In this email, you've got a subject line, of course. Then you've got an embedded MP3 clip, which is unstructured. There's a photograph in there, a JPEG photo, which is unstructured data. And then there's an Extreme Networks logo, which is also a photo file, which is unstructured. And it's the ability to use techniques to index and analyze unstructured data that's providing new types of information to the world. And some of the techniques might include facial recognition or optical character recognition or techniques like that. So moving along to the next slide. So now we've got all this data and we can process it. What's it useful for? And again, those of you that are very familiar in the high-performance computing community, you're probably very, very familiar with many of these types of applications in financial services, in transportation, health and life science, and even in entertainment, the ability to transport massive amounts of data and do interesting things with it. So moving to number 8, another driver of the interconnect, and something that drives the challenge for that interconnect, is that over the past decade, or a little more than a decade, we've moved from single processor systems to clusters of processors. And you can see on this chart, which is from the top 500, about a year ago, I believe, is when this data point was taken. More than 80% of the top 500 are clusters of many single or multiple processor cores, but clusters of single computers to create a large virtual computer. And when you think about it, an HPC architecture or a big data architecture is kind of the opposite of server virtualization. It's taking many machines, clustering them together to create one logical machines, which is kind of the opposite of server virtualization in an enterprise type of application. So moving along to slide number 9, there's an equivalent Moore's law, or an analogy to Moore's law in high-performance computing. And we see that in this chart that the I/O doesn't quite keep up with compute and with the storage architectures or speeds and capacities. And so I/O tends to move back and forth between different techniques in the top 500. And what I've observed over the last 5-10 years is that InfiniBand and Ethernet kind of leapfrog each other over time in high-performance compute interconnect architectures or the interconnects themselves. So moving to slide 10, what are those interconnect challenges? Well, first of all, massive scalability. And again, we talked about how these HPC clusters are clusters of many, many machines, hundreds, even thousands of machines that all need to be connected. And the storage in those clusters is sometimes centralized, and sometimes it's embedded within each of the rack-mounted servers. So the ability to scale massively in both bandwidth and in just absolute port counts. The ability to manage it and manage it more efficiently. Convergence of one common network infrastructure can sometimes make these HPC clusters easier to manage rather than using separate interconnect technologies for storage versus the message passing interface or MPI traffic versus the data traffic versus the interconnect that's used to present the result to the end user. And in large HPC clusters, energy is constantly a challenge and a concern. I've read estimates that the interconnect is roughly 15 to 20% of the energy, but it's still significant. And then availability. There are certain types of HPC applications where getting that result is time sensitive and urgent. And so we need to look at architectures that can tolerate the failure of a link within the network or the failure of a port within the network and recover quickly. Moving on to slide number 11, some of the network level considerations for big data is the processing time. And not all HPC applications are super time sensitive, but many of them are. And so that's where latency comes in. The barrier synchronized computation means that certain types of parallelized operations, you need to complete one cycle before you move on to the next cycle. And that's where a low latency interconnect comes into play. Traffic burstiness and data volume drives the need for big fat pipes, for higher speed pipes. And we'll see as we talk about Ethernet more specifically that 40 gigabit Ethernet is now the norm, and 100 gigabit is coming online quickly. Moving on to slide number 12, top 3 requirements for HPC interconnect fabrics. Throughput. So again, that non-blocking performance. And not all architectures are fully non-blocking. Typically on the storage side, you'll see non-blocking. On the server side, you may see non-blocking, or you may see 3-to-1 oversubscription, or even 7-to-1 oversubscription, depending on the type of workload and analytics that are being performed. Bandwidth, as we talked about, to handle the volumes of data and the burstiness of the data, continuing demand for higher speeds. Many of the top 500 supercomputing machines are still using gigabit Ethernet, but in our own business, we're seeing more and more servers being connected by 10 gig, and then using 40 gig as the uplinks, and we're beginning to see storage connected directly with 40 gig Ethernet, whether that be iSCSI-based storage or fiber channel over Ethernet. And then finally, the latency. And what we'll see later on is that the latencies of Ethernet switches today using cut-through switching are in the 500 nanosecond type of a range, so closely approaching the speeds of InfiniBand or the latencies of InfiniBand. Moving on to slide number 13, I/O technology to meet the future demand. So to bridge this gap, we need very scalable bandwidth, flexible bandwidth, economical, and reliable, and we talked about that. Moving to slide number 14, let's look at HPC IO technology alternatives. In this chart, the bubbles on this chart change as we go through future generations of technology. And again, some of the key attributes: scalability, bandwidth, latency, but also flexibility, reliability, and we can't ignore economics. But Ethernet has made great strides in this area over the past 3 or 4 years. And if I were to look at this chart before today's Ethernet technology, the bubbles on the right column there, the Ethernet column, would not be as fully filled as they are today. So Ethernet today with 40 gigabit and the new cut-through switching offers tremendous scalability, tremendous bandwidth, latency, as I said, that approaches that of InfiniBand, flexibility, reliability, and economics. So I want to talk a little bit more about reliability and how there's a confluence of technology within Ethernet that now makes iSCSI and fiber channel over Ethernet a real viable alternative to FCOE as a storage interconnect. And we've heard about FCOE for at least half a decade, and we've talked about iSCSI for over a decade, but they haven't really caught on. And I think that's because Ethernet has continued to be missing a couple of key components of the technology, which now is there. So the 3 components that I'll talk about are absolute speed, latency, and then the reliability of the underlying fabric, and the fabric being the links that interconnect the switches together. And what we've seen with Ethernet is it's now faster than fiber channel. A few years ago, we had 8 gig fiber channel and 10 gig Ethernet, and they were pretty darn close to each other. Now Ethernet, 40 gigabit Ethernet is quite mature, and fiber channel is running at 16. There's a 32 gigabit proposal on the table, but we're still at least a year away from commercial availability of 32 gigabit fiber channel. The latencies with the new cut-through switches are well under a microsecond per hop in an Ethernet network. The latest switch that Extreme just introduced has less than 600 nanoseconds of port-to-port latency. And finally, a more important component, I think, that's prevented iSCSI and fiber channel over Ethernet from really taking hold is that fiber channel is fundamentally a reliable network infrastructure in that all of the links between switches, the capacity of those links are used, and there's very fast failover if one of those links were to fail. Ethernet has had to overcome some of the limitations of spanning tree, and there are now fabric technologies such as Trill, which is transparent interconnection of lots of links, or shortest path bridging, or some of the proprietary fabric technologies from Cisco like FabricPath or Juniper's QFabric, but now they're the industry standards such as Trill and shortest path bridging that make that underlying fabric technology incredibly reliable, very fast healing, or very quickly healing in the event of a failure. And those 3 components, I think, make Ethernet a really viable interconnect for the storage side of an HPC cluster. So moving on to slide number 15, the orange color here is gigabit Ethernet. 10 gig is a thinner slice within this stacked chart here. InfiniBand is the kind of goldenrod yellow color there, and you see that they're pretty equivalent. On slide number 16, I actually took a look at the latest Top 500, which came out a few weeks ago in November. And what I was able to glean is that 212 out of the top 500, or 42.4%, are running Ethernet in the interconnect. And of the top 500, it's 41.2% that are running InfiniBand. So again, every other top 500 InfiniBand and Ethernet tend to kind of leapfrog each other, but we're seeing Ethernet carry a big portion of the top 500. And I would postulate that if you look at 500 and greater in terms of machine sizes, you'll see more and more Ethernet just because of the cost advantage and the operational advantage that Ethernet brings to that HPC interconnect. Moving to slide number 17, one of the advantages that InfiniBand has had is had the direct memory access, the RDMA capabilities. And with RDMA over Converged Ethernet, known as RoCE, we're now seeing Ethernet continue to evolve and adapt to support that same kind of high-performance capabilities that we've seen in InfiniBand and other proprietary interconnects in HPC. So Ethernet, this 40-year-old interconnect technology, continues to evolve, continues to adapt, and continues to be applicable to more and more types of applications. So wrapping up here, I'll share with you a couple of sample architectures. The first one here on slide 18 is a typical architecture that has centralized storage and is using 10 gig top of rack switches at the access side, accessing the compute cluster nodes, and using a core of core switches. The next slide, 19, is a little bit more detailed example of this, showing top of rack switches on the compute nodes connected by 10 gigabit up to it's a spine leaf type of an interconnect structure where the leaves are those top of rack switches at the top of the compute nodes. The storage nodes, which is centralized storage, is connected directly into the spine at 40 gigabits. And this creates a very, very scalable, high-performance fabric that can support, literally thousands of machines and tens of petabytes of storage, if not more. And then slide number 20, the cluster interconnect fabric options. With some of the new switches coming onto the market that support up to 32 40 gigabit ports, and those 40 gigabit ports can actually be broken out into 4 by 10 gig ports using breakout cables. Just using these 1U top of rack type switches in a spine and leaf architecture where I'm using the same switch as both a spine and as a leaf, I can create very, very large, very, very high performance structures in a very, very small footprint. So the architecture at the top, commonly called a fat tree or a close architecture, that particular architecture is a fully non-blocking architecture that supports 256 10 gigabit connected servers, and in this case, the storage is direct attached into each server node. And then 4 of the switches are used as leaves, and 2 are used in the spine. And you can do this in 6 rack units of space with very, very low power consumption and less than 1.8 microseconds of latency port to port, any port to any port, because the latency across a single box is less than 600 nanoseconds. If my workload is such that I can oversubscribe the servers, I can build a much larger structure. The structure at the bottom is using 10 of these 1U switches. So again, a footprint that's smaller than a typical chassis-based system, supporting 768 10 gigabit connected servers with a 40 gigabit backbone. And again, this is just a couple of examples of the types of interconnects you can use today using the very high performance, low latency Ethernet technologies that are available today. So to summarize, Ethernet is catching up to the proprietary interconnects and to InfiniBand in latency, in bandwidth, and in fact surpassing it, certain technologies in bandwidth. And it continues to evolve and adapt to a variety of applications, including high-performance computing applications. And the other advantage that we never should forget about Ethernet is there's a huge installed base of people that know how to manage it and then how to run it, just because of the ubiquity of the technology. And with that, Rich, I'll hand it back to you if you've got any questions for me.
Well, absolutely. Thanks, Derek. At SC13, we were both there a couple weeks ago. and I happened to moderate a panel on virtualization for HPC, and the question was, will it ever really get here? And I asked the panel, will we even need a session like this in 5 years? And they said, no, no, no. In 2 years, everyone will be using virtualization on this show floor. They were very, they had, a unanimous kind of a thought there. How well would that play in with Ethernet, seeing that you have much more maturity there in that technology with virtualization? What do you think?
Sure. So virtualization has lots of different meanings, of course. We've talked about server virtualization for a long time, and I know some HPC examples use clusters of virtualized machines. But on the networking side, virtualization is, of course, a more nascent technology, and we're seeing, of course, software-defined networking using southbound interfaces such as OpenFlow and others, but also the northbound interfaces and more of the orchestration level management of the network itself. And that's where I think some of the flexibility of software-defined networking can play a role in HPC architectures, especially with orchestration applications such as OpenStack, where you can much more flexibly manage and configure a network in a more virtualized manner. And this would be useful for organizations that run a large HPC cluster but run many, many different types of workloads and share that cluster amongst different departments or different types of applications.
So we didn't talk much about Extreme here, Derek. Do you guys break out your business in terms of HPC versus data center, and just how important is HPC to your business?
Yeah, so we have some very flagship accounts in HPC. The National Center for Supercomputing Applications in the United States, for example, is one of them. We have a number of oil and gas companies in the Middle East that use our, and also in Asia, that use our BDX8 and are looking at our new X770, which is the low latency 40 gig switch. They're already using our 670 10 gig switch for doing seismic evaluations for where to drill for oil. So HPC is an important part of our business. The part of the whole Ethernet world that is HPC is probably less than 5% of the Ethernet interconnect, but it tends to be a very leading edge part of the technology in terms of speeds, latencies, and bandwidth and cluster size or fabric size. One of the things we've observed is that our HPC customers tend to refresh on a 2 to 2.5 year cycle, just because the servers refresh so quickly, and two, the kinds of workloads that people are dreaming up for HPC continue to evolve very quickly. This is in contrast to our enterprise business, which is about 3/4 of Extreme's business, where the refresh cycle is more like 5 to 7 years. So HPC is a very important part of our business for a couple reasons. One, it generates a lot of revenue, but two, it drives Extreme to continue to lead in performance and next generations of technology and capability.
Yeah, yeah. So looking forward, then, I wanted to share a story. A panel, I think 2 years ago, Don Becker, one of the Beowulf founders, they asked him, what will the interconnect be for an exascale system? And he says, I don't know, but it'll be called Ethernet. So would you agree with that? And do you see Ethernet continuing to evolve to potentially that level?
When I get asked that question, I look back at my own career in networking.
Yeah.
And I started my career in networking in the mid-'90s with a technology called frame relay, and then a technology called ATM. And then I joined a storage networking company in the early 2000s with a technology called fiber channel. And the networking technology that continues to live on and continues to adapt and continues to evolve is Ethernet. These other technologies live, and they live for a long time, but eventually they decline. Token ring, AppleTalk, X.25, frame relay, ATM, fiber channel is either growing at low single-digit rates or maybe even finally declining, although its decline was predicted 5 years ago or more. it is flattened out for sure, maybe declining. Ethernet continues to grow, and every forecast that I've seen looking into 2017, 2018 shows a cumulative growth rate between today and then of still another 25% of growth. So Ethernet is the technology that continues to evolve, and that's exactly what the tagline I have on that slide is: Ethernet evolves. That's what it does.
All right. Well, Derek, I can't let you go without asking about your band. What's your band called?
You know, the band is called Fill in the Blanks, and our lead singer is Phil.
Yeah.
And that makes me a blank, I guess. But we play classic rock from the 70s and 80s. It's a cover band, and we play local clubs and some private parties here in the Silicon Valley, and it's a lot of fun. It is a good outlet from the stress and strain of Ethernet technology on a day-to-day basis, but it's also related in some ways. And audio-video bridging is a topic for maybe another webcast someday, Rich. And we can talk about how Ethernet is evolving and adapting to carry multiple video streams and audio streams on a common piece of fiber optic cable, and getting rid of all the massive cables that I set up every gig for my band. Doing it all over Ethernet, guaranteeing bandwidth and latency and synchronizing multiple streams. Pretty interesting stuff.
Well, yeah.
Ethernet continues to evolve.
Yeah, moving a lot of data. So that's terrific. Well, Derek, I want to thank you once again for coming on the show today.
Rich, thank you very much.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.